All right, so what about S Hmax? All right. So if we go back to those Kirsch equations and we assume that delta P is normally we have the mud pressure minus the pore pressure. But let's assume that we can somehow figure out what the mud pressure is right at the point of fracture initiation. We'll call that the breakdown pressure, right? So this is the instant of fracture initiation. Call that the breakdown pressure. Well, then if we plug that into the equations, where we've again assumed that fracture initiation will occur at the tensile stress, okay? So this could be 0, or in the case that it's not 0, you'd have some value, some small value there. Then you have this equation, and if, okay, so assuming that you've measured S-min in some way, right? From a mini-frac leak-off test, you have S-min. Now you can tell right when the crack is initiating at the wellbore. You have the breakdown pressure. You can estimate or measure the pore pressure, and you can estimate or measure T0, measure from an experiment in the laboratory. Then you could theoretically solve for S Hmax, and you have an estimate of S Hmax. There was one if you look in the Zobac's book, you can refer to the paper, but there's others that have proposed this, where this is if you initiate a fracture first, such that now the tensile strength of the rock, and you can determine when the breakdown pressure. So you've already initiated a fracture, and then you can measure or figure out what the breakdown pressure is after that fracture has been initiated. Then you can sort of eliminate the need to measure or estimate T0. And so you have this simplified equation. So then you need to measure or estimate the pore pressure, measure SH-min, and you can figure out S-max. In theory, okay? Does this work very well? Well, let's consider, and I hate that my fractions aren't showing up. Let's consider a system that has this compressibility. And if you remember, we talked about compressibility. It's like the inverse of the bulk modulus. This time we're talking about the compressibility of the entire system. So the compressibility of the fluid that we're using, the pumps, everything that's in the assembly, right? All the total compressibility of the entire system that we're using to pump in water. And I wrote this in a way that should be obvious. So if you remember, the compressibility is like the volumetric strain divided by the volumetric stress. Right? Well, in this case, the volumetric strain is the change in the total volume of our system divided by its original volume. And then we divide that by a change in pore pressure. A change in pressure in delta P. Okay? So if we solve for this equation for delta P, oh gosh. Oh, there it is. So if we solve this equation for delta P, we have this, right? And then we're going to divide both sides by delta T, which is valid, right? We can manipulate equations as long as we do the same thing to both sides. And so let's see what this equation is telling us. It's telling us that the change in pressure, right, that's the left-hand side, the change in pressure with respect to time, which is what we are looking at on the curve, right? Right, that's what we're looking at is pressure versus time. Right? So the change in pressure versus time is proportional. The proportionality constant is the bulk modulus divided by the initial volume, basically, or the 1 over the compressibility times the initial volume. So it's proportional to the change in volume. Okay. So we're looking for a change in pressure, because that's what we're measuring. That's proportional to the change in volume. And we're looking for the change in volume associated with initiating a fracture. Well, think about the volume of water or fluid associated with drilling. right? We're talking about thousands of gallons, okay? And we're looking for the pressure change associated with initiating a tiny little fracture, because it has to be right at the initiation point. So the volume associated with this little tiny fracture in comparison to the total volume, it's nothing, right? It's indetectable. And so in reality, you can never actually figure out what that breakdown pressure is because you won't see it. You won't see it. So in a leak-off, the difference is between what I'm saying here and a leak-off test is that the leak-off point in a leak-off test, we're looking there for the minimum. So a fracture is always going to propagate, not initiate, but propagate in the direction perpendicular to minimum horizontal stress, right? So in the leak-off test, where we see that inflection point that we call the leak-off point, that's the part where we know that there's a fracture propagating. It's propagating, okay? It could have initiated well before that. We just never saw it because of this very scenario here. So we can't see the initiation point, okay? What we can see is that it's clearly propagating. At that point, there's enough volume change there associated with the fracture that you can see the change in pressure, and then you see that inflection point, okay? The other sort of complication associated with finding S Hmax is that the Kirsch equations, again, are only valid for a circle. And, once you get to some depth, so this might work in a very, very controlled way where you have very good measurements at shallow depths where volumes are small and breakouts are not likely, right? But once you get to certain depths, then you always have some amount of breakouts, and at that point, your Kirsch equations aren't valid, and so you can't really determine when the initiation point is. Right? We can still determine what the minimum horizontal stress is, because once a fracture is propagating, we can look at the fracture propagation pressure, we can look at the shut-in pressure, but that's different. With the maximum, we really need to know right at the initiation, and it's really, really hard to find. Right? So the answer is not very well.
So I guess we're overestimating the minimum pressure, right? So what's like the order of magnitude of that? Like the actual initiation point, how much different is that than like what we're estimating?
Well, it's hard to know because your fractures initiate at the tensile strength of the material, right? So in theory, it would be the difference. But in reality, there's a lot of flaws in rocks. And so fractures in this case, there's always some little micro flaws or whatever that get activated through mechanisms that aren't really associated with the strength of the rock. They're associated with the toughness of the rock. And you might say, well, what's the difference? But there actually can be a lot of difference. And it comes from, right, so if I have a stress-strain curve, the strength is basically, when we talk about the strength, it's basically the peak of the stress-strain curve, right? So if I give you a stress-strain curve like that and I asked you, how strong is this rock? Okay, well, it broke right here. This vertical line indicates failure. So the strength of this rock, you'd tell me, is that. This is the strength of the rock. Okay. If I asked you how tough is the rock, what would you tell me? No, that's the modulus. Toughness is a measure of energy absorption, right? So think about Physics 101, right? In Physics 101, you learn about work. What is work? It's like force times a distance, right? Well, stress is just a normalized force. Strain is a normalized distance, right? So, actually, the correct correct definition of work is the integral of force times ds, where s is a path length or distance, right? So in this case, it's actually a work per volume or an energy density, but it's the same idea. It's the integral of stress strain. So the area under the stress strain curve. This is the toughness of the material, and the material's toughness is directly related to how well it absorbs energy, or another way to say that is how well it resists fracture. And they're not one and the same. A material that is strong is not necessarily tough. And I'll give you an example. It's not typical in rocks that you'd see this difference, but let's just go to an extreme example. I mean, I could I can have a material like, say, copper. Well, that's not a good example. Let's say, well, let's not come up with a material. Let's just say I have a material that, because I don't want you to go like look up the values in a book and come back and tell me, oh, you were 1% different in your analogy. Right? But the idea is that I can have a material that can be tough but not necessarily strong. And tough materials are ones that can absorb energy, and these are actually like plastic materials, right? So a plastic material, if I begin to deform it, if at some point, I may end up with something like this. Well, this area under this curve, the red, is clearly a larger area than the blue, right? So the red material is tough, but it's not as strong as the blue material because it never reached that peak. It never reached the peak, right? So I used to, when I did a lot of ballistic impact stuff, this is very important, right? Because you can have materials that are very tough, and they can stop a bullet, right? Problem is, if you're wearing it on your body, who cares if it can stop a bullet if it takes 20 feet to stop it? Because it's not going to help you, right? So what you want for armor is materials that is both tough and strong, right? They can absorb energy, but is stiff enough that it doesn't, take 20 feet or your entire body to do it. So anyway, I got really sidetracked there. But to go back to your question, it's really kind of too complicated to answer because fractures can propagate associated with the toughness of the material, which is not one and the same with the strength, which is what you measure, in the laboratory in unconfined compressors. Okay. See you Thursday.